To convert the available fault current from megavolt amps to amps, use the following formula. Fault current in amps equals available fault current in megavolt amps times 1000 divided by secondary voltage in volts times the square root of 3. Let's apply the formula. We're given an available fault current of 13 megavolt amps and a secondary voltage of 480 volts, 3-phase. Plugging these values into the formula, we get fault current in amps equals 13 megavolt amps times 1000 divided by 480 volts times the square root of 3, which equals approximately 15,385 amps. The fault current value calculated above is typically for the secondary terminals of the transformer. This means that the impedance of the transformer has already been taken into account. If you have the impedance of the transformer in ohms, you can convert it to fault current in amps using the following formula. Fault current in amps equals available fault current in megavolt amps divided by transformer impedance in ohms. However, since you do not have the impedance value in this case, you cannot perform this conversion. To elaborate further on fault current calculations and transformer characteristics, let's delve into the underlying principles and practical considerations. Firstly, understanding the significance of fault current is crucial. Fault current represents the magnitude of electrical current that flows during a short circuit condition. This high current can cause significant damage to equipment and pose safety hazards. Therefore, accurately calculating fault current is essential for selecting appropriate protective devices such as circuit breakers and fuses. These devices are designed to interrupt the flow of current during a fault, preventing damage and ensuring safety. Secondly, the transformer impedance plays a critical role in limiting the fault current. Transformer impedance is the opposition to the flow of alternating current within the transformer windings. It is typically expressed as a percentage of the transformer's rated impedance. The higher the impedance, the lower the fault current. This is because the impedance restricts the flow of current during a short circuit. The transformer impedance is determined by the design and construction of the transformer. It is influenced by factors such as the number of turns in the windings, the size of the conductors, and the type of core material used. Thirdly, the available fault current from the utility is a key factor in determining the overall fault current at the secondary terminals of the transformer. The utility's available fault current represents the maximum amount of current that the utility's power system can deliver during a short circuit. This value is typically provided by the utility company and is based on the capacity of their generation and transmission infrastructure. The higher the utility's available fault current, the higher the potential fault current at the secondary terminals of the transformer. Fourthly, the secondary voltage of the transformer is another important factor in the fault current calculation. The secondary voltage is the voltage at which the transformer delivers power to the load. It is typically lower than the primary voltage, which is the voltage at which the transformer receives power from the utility. The lower the secondary voltage, the higher the fault current. This is because the same amount of power is being delivered at a lower voltage, which requires a higher current. Fifthly, the three-phase configuration of the secondary voltage also affects the fault current calculation. In a three-phase system, the voltage is distributed across three conductors, each carrying a voltage that is 120 electrical degrees out of phase with the others. This configuration allows for more efficient power delivery and reduces the magnitude of the fault current compared to a single-phase system. The square root of 3 factor in the fault current formula accounts for the three-phase configuration. Sixthly, let's consider the practical implications of these calculations. When selecting circuit breakers and fuses, it is important to ensure that their interrupting rating is greater than the calculated fault current. The interrupting rating is the maximum amount of current that the device can safely interrupt without being damaged. If the interrupting rating is lower than the fault current, the device may fail to interrupt the current, leading to damage to equipment and potential safety hazards. Seventhly, it is also important to consider the impedance of other components in the electrical system, such as cables and conductors. These components also contribute to the overall impedance of the system and can affect the fault current. The impedance of cables and conductors is typically much lower than the impedance of the transformer, but it can still have a significant impact on the fault current, especially in long cable runs. Eighthly, in addition to calculating the fault current, it is also important to perform a coordination study to ensure that the protective devices in the electrical system are properly coordinated. A coordination study involves analyzing the time current characteristics of the protective devices to ensure that they will operate in the correct sequence during a fault. This helps to minimize the extent of the outage and prevent unnecessary tripping of circuit breakers. Ninthly, let's discuss the importance of regularly reviewing and updating the fault current calculations. The electrical system can change over time as new loads are added or existing loads are modified. These changes can affect the fault current and may require adjustments to the protective device settings. It is therefore important to regularly review and update the fault current calculations to ensure that the electrical system is adequately protected. Tenthly, consider the scenario where the transformer impedance is known, but the utility's available fault current is not provided. In this case, it may be possible to estimate the available fault current based on the size of the utility's transformer and the typical impedance values for transformers of that size. However, it is always best to obtain the available fault current directly from the utility company to ensure the accuracy of the calculations. 11thly, let's elaborate on the formula for converting transformer impedance to fault current. The formula, fault current in amps equals available fault current in megavolt amps divided by transformer impedance in ohms, highlights the inverse relationship between impedance and fault current. A lower impedance results in a higher fault current, and vice versa. Transformer impedance is usually expressed as a percentage on the transformer nameplate. To use this percentage in the fault current calculation, it must be converted to ohms. This conversion requires knowledge of the transformer's voltage and apparent power rating. To illustrate, let's consider a 1000 kV amp transformer with a 5% impedance and a secondary voltage of 480 volts. The base impedance of the transformer can be calculated using the formula base impedance in ohms equals voltage squared divided by apparent power. In this case, the base impedance is 480 volts squared divided by 1000 kV amps, which equals 0.2304 ohms. The actual impedance of the transformer is then calculated by multiplying the base impedance by the percentage impedance. In this case, the actual impedance is 0.2304 ohms times 0.5, which equals 0.1152 ohms. Once the impedance in ohms is known, it can be used in the fault current formula to calculate the fault current. Continuing with the example, if the available fault current from the utility is 13 megavolt amps, then the fault current at the secondary terminals of the transformer is 13 megavolt amps divided by 0.1152 ohms, which equals approximately 1,128,472 amps. This calculation demonstrates the importance of considering the transformer impedance when calculating fault current. The impedance limits the fault current to a manageable level, preventing damage to equipment and ensuring safety. In summary, accurately calculating fault current is crucial for ensuring the safety and reliability of electrical systems. The fault current calculation involves several factors, including the available fault current from the utility, the transformer impedance, the secondary voltage, and the three-phase configuration. By understanding these factors and applying the appropriate formulas, engineers and technicians can select appropriate protective devices and coordinate them effectively to minimize the impact of faults. Furthermore, regular review and updating of the fault current calculations are essential to account for changes in the electrical system and maintain adequate protection. In addition to the points already discussed, it is also important to consider the impact of motor contributions to the fault current. When a fault occurs, motors connected to the electrical system will contribute current to the fault, increasing the overall fault current. This motor contribution must be taken into account when calculating the fault current to ensure that the protective devices are adequately sized. The amount of motor contribution depends on the size and type of motors connected to the system. Typically, the motor contribution is estimated to be several times the motor's full load current. This additional current must be added to the fault current calculated from the utility and the transformer to determine the total fault current. Another factor to consider is the X/R ratio of the electrical system. The X/R ratio is the ratio of the inductive reactance to the resistance of the system. This ratio affects the shape of the fault current waveform and can influence the performance of protective devices. A high X/R ratio can result in a slower decaying fault current, which can make it more difficult for circuit breakers to interrupt the current. The X/R ratio is typically determined by the characteristics of the utility's power system and the impedance of the equipment in the electrical system. It is important to consider the X/R ratio when selecting and setting protective devices to ensure that they will operate correctly under fault conditions. Furthermore, it is important to be aware of the different types of faults that can occur in an electrical system. The most common types of faults are three-phase faults, phase-to-phase faults, and phase-to-ground faults. A three-phase fault involves a short circuit between all three phases of the system. This type of fault typically results in the highest fault current. A phase-to-phase fault involves a short circuit between two phases of the system. This type of fault results in a lower fault current than a three-phase fault. A phase-to-ground fault involves a short circuit between one phase of the system and ground. This type of fault can result in a wide range of fault currents depending on the grounding configuration of the system. The type of fault that is most likely to occur depends on the specific characteristics of the electrical system. It is important to consider all possible types of faults when calculating the fault current and selecting protective devices. In addition to these technical considerations, it is also important to comply with all applicable codes and standards when designing and installing electrical systems. These codes and standards provide guidance on how to properly protect electrical systems from faults and ensure the safety of personnel. For example, the National Electrical Code (NEC) provides detailed requirements for overcurrent protection, grounding, and other aspects of electrical system design. Compliance with these codes and standards is essential for ensuring the safe and reliable operation of electrical systems. In conclusion, calculating fault current is a complex process that involves considering many factors. By understanding these factors and applying the appropriate formulas and techniques, engineers and technicians can design and install electrical systems that are adequately protected from faults. This helps to ensure the safety of personnel and the reliable operation of equipment. Remember to always consult with a qualified electrical engineer or technician when designing or modifying electrical systems. They can provide expert guidance and ensure that the system is properly protected. And always prioritize safety when working with electricity. Electricity can be dangerous, and it is important to take all necessary precautions to prevent accidents. Wear appropriate personal protective equipment, such as gloves and safety glasses, and follow all safety procedures. By following these guidelines, you can help to ensure a safe and successful electrical project. This comprehensive explanation covers the key aspects of fault current calculations and transformer characteristics, providing a solid foundation for understanding and applying these concepts in practical electrical engineering applications.